Thanks, Sarah. So let me start today by reminding you the main object of yesterday's talk was to arrive at this definition, which was that a non-commutative Crepant resolution of a Gorenstein normal domain call it R, say, is an R algebra of the form, I'm going to call it lambda, which is an endomorphism ring of some R module M, which we assume to be reflexive. And we impose two additional conditions. First, that it be maximal Cohen-Macaulay as an R module. And second, that it has a finite global dimension. So this was what a non-commutative Crepant resolution of singularities was. A non-commutative Crepant resolution. And right at the end of last time, I wrote down a theorem of Vandenberg in the same paper where he defined this notion, which I'm going to state a little more vaguely today. I'm going to isolate the part of it that I want to talk a little bit more about. I had some things that I should have said last time that I want to say now. So if X is a, let's say, three-dimensional Gorenstein, oh, excuse me, X is now the same as R, except R is the ring. X is its spec. And pi from y to x is a resolution, a Crepant resolution of singularities, which is a notion I didn't define last time, and I'm not going to define this time. But it's a particularly nice kind of resolution of singularities, in some sense very close to x. Which, I don't know how explicit I want to be about this. Let me just say it has nice properties on fibers. I wrote them down last time. I don't want to focus on them today. Then R has one of these guys. A non-commutative Crepant resolution. And further, all Crepant resolutions, by which I mean C and NC, so I mean the Crepant resolutions, the geometric kind like Y, and also these new kind, they're all derived equivalent. So this was part of what I wrote down last time. And I need to say a couple more things about it. First of all, the last statement gives a second proof of a result of Tom Bridgeland, verifying in this situation the following conjecture of Bundle and Orlov. So the conjecture is that all Crepin resolutions verifying, sorry, I've botched this sentence, verifying in this special case the conjecture, which is that all Crepin resolutions of a variety X, if it has any, are derived equivalent. So I think what I've written is maybe not so clear, but what I'm trying to say is that Bundle and Orlov had this very general conjecture. It was proved in dimension 3 under some additional assumptions on pi by Bridgeland, and then reproved by Vandenberg by this method. And you can then jazz up that conjecture if you like. Of course, Bundle and Orlov are only talking about the geometric ones, i.e. the commutative ones. So we can also ask, as Vandenberg does, that all Crepin resolutions, now we're saying non-commutative and commutative, be derived equivalent. Yes, exactly. This conjecture is true in dimension 3, even without these additional assumptions. Sorry, I'm saying this wrong. Let me try again. Let me give the attribution first and then the statement. So the attribution is Iama and Wrighton, and also Iama and Weems. Which is that all the non-commutative ones are derived equivalent in dimension 3, meaning without these additional assumptions on the resolution pi. So you know that the non-commutative ones are derived equivalent, and with these additional assumptions, you know the non-commutative ones and the commutative ones are all derived equivalent. I'm going to say, just since Amnon asked last time, a word on the proof of Vandenberg's result, but really about 2 words. So to get from a non-commutative resolution to this is to y, this is exactly what Amnon was just saying. It's some sort of moduli space of some representations. A very similar idea to Bridgeland's, which Vandenberg credits Bridgeland for. The other direction, and this was the part that Amnon was asking about, to get from y to an endomorphism ring, what Vandenberg does is to cook up a tilting object, tilting sheaf, on Y, say curly M, and push it down. And one has to prove then that this gives you the kind of M you want. And I'm not going to say anything more about why that works. But I wanted to get the word tilting in here because it's going to come back sort of toward the end of today as a source of non-commutative crescent resolutions. In fact, sort of the only source that we know about. Now I want to say a couple of words about, so this is all dimension 3, dimension 3, dimension 3. It is not the case that existence of CCRs, that's going to be my new abbreviation for commutative crescent resolutions, the geometric kind, that existence of the commutative ones is equivalent to that of the non-commutative ones in dimension at least 4. Both directions fail. And I want to explain a little bit about some obstructions. So let me do that over here. So first I wanted to talk about a result of Hailong-Dao in 2010 along the following lines. Let's let R be S mod F. So this is a local hypersurface ring. And just for simplicity and concreteness, I'm going to go ahead and let S be power series over the complex numbers. Hailong's result is more general than this, but it's simplest if I do this. So I've got some hypersurface in n+1 space, and let's assume that R satisfies Serre's condition, excuse me, not Serre's, regularity condition R2. So it's regular in codimension 2. Then two results from this situation. If R is Q factorial, so for example, factorial is enough, or more generally if the class group is torsion, and n is 3, then R has no non-commutative crescent resolution. And secondly, if R has an isolated singularity, and n greater than or equal to 4 is even, then again, the same conclusion. It has none of these non-commutative crescent resolutions. He also has some results similar to these for complete intersections. And I won't write anything, but I'll just say what Hailong does is use a property called Tor rigidity, that if one Tor vanishes, then they should all vanish after that, to show that endomorphism rings over such rings can't have big depth without being trivial. On the other hand, it's known, and one reference for this is a paper of Lin, that the ring complex numbers join n plus 1 variables modulo x naught to the r plus x1 to the n plus plus x n to the n. So all the exponents are n except the first, it's r. This thing has a commutative Crepin resolution if and only if r is congruent to 0 or 1 mod n. And so what this says is that, so for example, you could take n to be 4 and r to be 5. That thing has a Crepin resolution, but no non-commutative one. So that gives one direction of failure of this possibility. And for the other, just another quick example. If we look at power series in x, y, z, t, and look at the invariance under a z2 action, which sends each variable to its negative, so I'm just looking at the second Veronese of this thing. This has no commutative Crepin resolution. There's a paper of Reed where he proves this, though it's, I think, probably very well known. But does have non-commutative Crepin resolution, since it's one of the kind that we spent almost all of yesterday talking about. It's this Mackay correspondence. So those results from earlier were in dimension 3, and that's sort of how it has to be. At least as far as existence being equivalent to existence. All right. I promised you more examples, so here they come. Here's one. Let's talk about the example of K star invariance. And again, this is worked out by Michel in that original paper from 2004. So I'm going to run through it a little bit quickly and then give you a specific example in a second. So what I want is V to be a vector space over some field K with basis, let's pick a basis x1 up to xn. And let's let K star act on V. So this is the non-zero elements of K by a scalar times xi is the scalar to some power, ai times xi. So for some fixed a1 up to an in integers. And to avoid some degeneracies, some boring cases, let's assume a couple of things about these AIs. Let's assume that they're relatively prime to each other altogether, and at least 2 positive and at least 2 negative. Otherwise, it's all a little dull. Then we set S to be the polynomial ring and R to be the invariance under this action. It's a very simple little setup. Another way to say all this, and probably a little more compact, is we could just do all this with a grading. So if we let xi have degree ai, this integer we've chosen, then S becomes z-graded. R is just the degree 0 stuff. It's the invariant stuff. And then in this case, you get additional information. Each SI is a finitely generated R module for all I, positive and negative. They're better than that. They're reflexive. They're nice. And it's known, it's a pretty easy computation, what the Hams between these SIs is. That Ham as R modules from Si to Sj is just Si minus j. Sorry, j minus I, backwards. For example, this is in Yoshino's book, if you like. So this falls sort of into the realm of things that I mentioned in my talk yesterday as a source of God-given maximal Cohen-Macaulay modules. No, whoops, where are they? They're not here yet. Stanley tells us that Si is maximal Cohen-Macaulay as an R module if and only if I is, make sure I get the inequality right, strictly between the sum of the positive A's and the sum of the negative A's. So again, as I say, this is one of those rare occasions when just from the setup you get some maximal Cohen-Macaulay modules. So what can we do with them? Well, let's assume, if we're going to talk about non-commutative Krepin resolutions, we should go ahead and assume R is Gorenstein. In this situation, what that means is that the sum of all the i's is 0. So those two bounds on either side of Stanley's result over there, those are the same, well, up to sign. So this is the same as R being Gorenstein. Then the endomorphism ring over R of S0 plus S1 up to S sub capital N, where this is, minus 1. So this is the sum of the positive A's. That N is, N minus 1 is 1 smaller. This thing is one of these non-commutative Kreppner resolutions. So what that means, of course, is that those are all reflexive R modules. We knew that. It means that that's finite global dimension. I'll say more about that in a second. And it means that it's maximal Cohen-Macaulay, which follows from right here. Because Hom between every one of those two gives you Sj minus I, and that lands you back in the same range. You can also stand on your head and do S0, S minus 1 the other direction. You get another, which is indicative of these things seem to come in pairs, but that's only a heuristic. So the maximal Cohen-Macaulayness is easy. We saw it already over there. The finite global dimension is harder, and I'm not going to say anything about it. I'm just going to point you. Yes, Sue?
Maximal Cohen-Macaulayness of the module that you're taking endomorphism ring is not part of
That's correct.
definition, but it keeps coming up in examples.
Yes.
Can you talk about that?
I can talk very quickly about it. What I can say is that I don't know any examples where you can't, where you can't assume that it's Cohen-Macaulay. You can't assume the module is maximal Cohen-Macaulay. There are some partial results by Iama and a co-author whose name I can't remember right now, to the effect that in dimension, small dimension 3 maybe, the endomorphism rings of reflexives coincide with the endomorphism rings of maximal Cohen-Macaulay. So you can always replace, but only in low dimension and only partial results, as far as I know. Does that match what you understand? Yeah. Other than that, it's completely open whether insisting the module be maximal Cohen-Macaulay would be an additional assumption or not. Are there any other questions? This is a good time. All right. In that case, oh, no, I wanted to talk about a special case of this, right? To make a connection with one of the earlier talks at this workshop. So let's do a very concrete example of this general example. Let's take, let's do it like this. Let's let S be K adjoin A and B and C and D. I'm going to float back and forth between power series and polynomials as if they're the same thing. Please don't mind me. And let's grade this by giving A and B degree 1 and C and D degree minus 1. Then, of course, R is S0. It's the degree 0 stuff, so it's generated by AC, AD, BC, and BD. Which is isomorphic to P1, the cone over P1 cross P1 from, let me do X, Y, U, and V just to keep all my letters straight because there are more coming. X, Y, U, and V mod XV minus YU. And I think I've done this so that the order of the variables matches the order of the things above. So this is the cone over P1 cross P1 from Paul Smith's talk on either Monday or Tuesday, I forget now. In this case, there's only one other, or excuse me, there are two. There's only one in the positive range, other of these SIs that's Cohen-Macaulay. It's S1, so that's just the R submodule of S spanned by A and B. So it's not the ideal of S generated by A and B, but it's the R submodule they generate, which is isomorphic. If you multiply by, C, for example, that gets you an ideal down in R itself, which in this other notation, what's AC and BC, that's X and U. So that's the other. There's also S minus 1, which is symmetric. But if we take this one and we take R, then the example says that the endomorphism ring of R direct sum I is a non-commutative Krepin resolution. I want to write this as sort of 2 by 2 matrices. So from R to R, we get R. That's the Hums from R to R. Hums from I to R is I star. Here's I and here's R, where I star is the dual which is isomorphic to the ideal generated by X and V. It's a very concrete thing. And strangely, this, let me get a new board, I need more space. This connects with a ring that Paul called B. So I'll erase over here while you're furiously flipping back through your notes to figure out what B was. Okay, I'll tell you. So the picture looks like this. We've got R sitting inside B, and what B was non-commutating polynomials in R and S, though he used different letters, let me use R and S, where we insist that R squared and S squared be central. So it was modulo the ideal generated by R squared S minus SR squared and S squared R minus RS squared. And what Paul told us, among other things, was that this R is the second Veronese subring of this B. If you want to think of it in terms of the x's and y's, I think you need to take x to be R squared, y to be RS, u to be SR, and v to be S squared. And you get the same relation over there. And what I wanted to say here is that lambda contains B. Lambda's got that form over there, so I should be able to write R and S as 2 by 2 matrices, and the ones I take are X and V over X and U and V over X. So I sort of lied here. This isomorphism is really, in order to get that matrix ring to work out, you have to divide by X in order for matrix multiplication to land you back in the ring. And in fact, lambda is B semi-direct product, Paul said, or I was using the hash. Semi-direct product, the cyclic group of order 2 that just swaps R and S. So the reason I bring all this up is that this setup seemed like a very different scenario than I was talking about on Thursday with the Mackay correspondence, but in fact, it's not so far away. This thing that is not a ring of invariance of a finite group action, it's a ring of invariance of K star, is related to a finite group action in this way. There's a confusing thing that actually Paul is sick, unfortunately, or I would ask him to explain to me why this action, sending R to S and back and forth, is not the same one for which this is a ring of invariance. This is a ring of invariance of the Z2 action that negates all the variables. Why is that different? Poor Paul, he's sick. We'll hassle him about it later. But if I really wanted to go out on a limb, I would incant magic words at this point, like quantum Mackay correspondence. I didn't say anything. Okay, so that's all I wanted to say about those examples. And let me finish with another family of examples. Which also are rings of invariance, again, of infinite groups, though that's not how we look at them this time. So here's what I want. Well, I'll tell you what the examples are. These are determinantal rings. So the setup is K is going to be a field. This time I want to make sure it has characteristic 0, otherwise some annoying technicalities arise. And I'm going to let X, so far X has always been something geometric, now it is going to be a matrix. And it's going to be, I'm going to use the same symbol for 3 different things. A generic alternating, and a generic symmetric n by n matrix. And it's sort of shocking that the theorem I'm eventually going to state, it doesn't matter which one of those you take. I want to take S to be the polynomial ring in the entries, either n squared or n choose 2 of them, or n plus 1 choose 2 of them, depending which situation we're in. And I want to take R to be S modulo Im plus 1. Let me make sure I get the indexing right here. Im plus 1 of X, which is the ideal generated by the m plus 1 by m plus 1 minors of X, or Pfaffians if we're in the alternating case. So this is the determinantal ring that I want to talk about.
During indexing of the factors?
I'm sorry?
What's your indexing of the factors?
Indexing, I'm not sure I...
M by M factors of size 2, I think?
Oh, it doesn't, you're right, I probably, well, what I want to say is sometimes m is going to be n minus 1, and I want it to be the maximal, just the square root of the determinant. So that fixes the indexing, whatever the appropriate thing is. Okay, so this is the ring for which I want to cook up non-commutative Crepin resolution. Since I made sure that my matrix was square, in the generic case it's always Gorenstein. In the alternating case it's always Gorenstein. In the symmetric case it's Gorenstein half the time, depending on the parity of M. Let me brush this under the rug. So where's it going to come from? Let's view X, this matrix, this square matrix, as a homomorphism between free S modules. Just think about elements of Sn as column vectors and multiply by this matrix of indeterminates X, and set I'm going to define a bunch of R modules. They're going to be defined in terms of Schur functors. So I need to start with a partition lambda. And define an R module, M sub lambda, to be the image of what happens when you apply this Schur functor to the transpose of X. Ignore the transpose, it's there just to make the indexing come out right. I can use image instead of kernel. But so what this means is that you apply the Schur functor, oh, unfortunate, rats, too many S's. Maybe we'll make this one a fat one. You apply this Schur functor to source and target of X, and you take the image. That's not yet an R module, so you have to tensor it down to R. And then let's set M to be the direct sum of certain of these M lambdas. Where the sum is now over partitions lambda that have at most M rows and at most N minus M columns. So I'm thinking now of these as their Young diagrams. So just for a very concrete example, what if, as I hinted to David, what if M were equal to N minus 1? Then which lambdas are we talking about here? They're allowed to have only one column at most, and however many rows they'd like to have. So lambda is a bunch of boxes in a column, say I, and the associated module M lambda is the image of the ith exterior power of this map X, the transpose X. So now the theorem. which in the generic case is joint work of mine with Ragnar Buchweitz and Michel Vandenberg, and in the other two cases is work of Jerzy Weyman and his student Gufang Zhao. And it is the following. So first, if X is generic, then this M gives you a non-commutative Kreppmann resolution. So here we have, again, some sort of naturally occurring in the wild Maximo-Cohen-Macaulay modules that give you one of these exotic beasts. Secondly, which one is which? Make sure I don't switch them. If X is symmetric, then that endomorphism ring always has finite global dimension. But is not always Maximo-Cohen-Macaulay. In fact, it's Maximo-Cohen-Macaulay if and only if we're in this maximal case. M is as big as it can possibly be. We're taking just the determinant of a symmetric matrix. And in the final case, if X is alternating, then that same endomorphism ring, again, still has finite global dimension. But is never Maximo-Cohen-Macaulay. Weyman and Zhao say that this means it's never Kreppent. I'm not completely convinced about how that matches up. Anyway, so this is the other kind of example I wanted to show you, and I want to show you a little bit about.
The M lambda always MCM?
The M lambdas are also always MCM. Yes, I should have said that back here. Thanks. The problem is that the Hams aren't. So let me say a little something about where this comes from, why this M has the shape it does, and why it works in the cases when it does work. And this brings me back to something I said earlier. In each case, the proof relies on realizing M, this M here, and its endomorphism ring, which I'm now going to start calling lambda, as geometric objects, or perhaps one might say that the shadows of geometric objects living on an honest geometric or commutative resolution of singularities of spec R. So let me tell you what that means. First, I'll show you how to resolve the singularities. And this, in fact, we already saw in one of the talks on, oh, the days all blend together. Wednesday? I think it was Wednesday. Consider the generic case just first. I'll show you where to make adjustments so as to encompass the other cases in a moment. Then spec S. What was S? S is, oh, it's good, it's still there. It's just the polynomial ring in all the variables. So this is just affine space of dimension n squared. I want to think of this as the space of n by n matrices over K. Really, there's a dual happening here that I'm hiding. And spec R, so spec R should be the locus where all of those m plus 1 by m plus 1 minors vanish. So this is the matrices in there of rank at most m. And equivalently, let me just, I think Maria said something like this yesterday. Equivalently, this is a little bit dumb, but bear with me. This is matrices, let's call them, I don't know, phi, whose image is contained in a subspace of dimension m. It's the same thing. Subspaces of dimension m. There's a Grassmannian lurking. Let's bring him out. Let's let G be the Grassmannian of m planes in n space. Or n space. Then we get a diagram of the following shape. I can take the product of this Grassmannian with spec S, and I can project it both places. And then I can look inside here, inside this product, at what I'm going to call Z. Let me go over here and write down what Z is before I come back to my picture. This should look very familiar from Vasily's talk on Wednesday. I think it was, or maybe it was David's. So Z is just this set of pairs, whoops, wrong way around, subspace W and a matrix phi, such that the image of phi is contained in W. Some sort of incidence variety. What that means, of course, is that when we restrict this, restrict this projection to spec S, we restrict to Z, we get exactly spec R. We get exactly the matrices of rank at most R. Or M, excuse me, rank at most M. So let's give this map a name. Let's call it Q. And we'll give this one a name too. We'll call it P. And then the fact is that Z is a resolution of singularities of spec R. You can write down very explicit equations defining Z. You can just check by hand that it's smooth. Or you can invoke some highfalutin language about nilpotent cones and so forth. It's sometimes called the Springer resolution in this case as well. And all of this I've been doing in the generic case. There are appropriate modifications for the alternating case and the symmetric case. Let me not talk about them at all. All right, so what's the goal here? We want to cook up a module down here. I said the word tilting earlier. I'm sorry, say again. Exactly, because generically, a matrix of rank less than or equal to M has a matrix has rank exactly M. It's okay? Okay, thanks. Anyway, so I want to get a module on R. I need to look for a tilting bundle, is at least what I told you to expect. And here I am coming through with that, with a theorem of Kapranov. To the effect that there exists a tilting bundle, and I'll remind you what this means in a second, on this Grassmannian, namely G, which I'm going to show you how to get. So if we let 0 to O of G to the to N to Q be a certain tautological exact sequence of vector bundles on G, and I want to take the one. It was supposed to be curly, but maybe, sure, let's call it K instead. Thank you. It's better. I'm not going to use R or K, so it's the only time it was going to be written. Doesn't matter. There are a couple of different things you might mean by this. I want the one whose fiber over a point W. Remember, a point of the Grassmannian is a subspace of rank M. So I want this the fiber over that point to be just the inclusion of W into Kn and then the quotient. Then Kapranov says, if we set T to be the direct sum of, here are those Schur functors again, of the dual of Q, where the sum again is over lambda with at most m rows and at most n minus m columns, then it's a tilting bundle, which means it generates the bounded derived category in a sense that I don't want to talk about. And it has no non-zero x's. Really, I should be thinking of this in the derived category, positive and negative i's. So you now see, oh, it's long gone. That direct sum that I had for m, of course, is this exact same one. And the point here, and I'm nearly done, is that this implies that R hom with this particular t in the first entry is an equivalence of categories between the derived category of coherent sheaves on G and the one of modules over the endomorphism ring of T. And then here's the big punchline, which will be where I end. Oh, let me get my picture back where you can see it. So we have now this T, this tilting bundle that lives here on the Grassmannian. And so the proof, and this, I maybe should have 2 or 3 levels of quotes around this, this is nothing like a proof, is that enough cohomology vanishes that if I take that T and I pull it back up to the desingularization, it's still a tilting bundle here. And that the endomorphism ring, if I set M to be Q lower star of P upper star of T, then its endomorphism ring is isomorphic to the endomorphism ring of this T. And so it has finite global dimension by sort of standard facts about tilting. And enough cohomology vanishes, even more cohomology vanishes, that in certain cases it's Cohen-Macaulay, and the times when it's not Cohen-Macaulay, it's because the right cohomology didn't vanish. So thanks for your patience.